Hi, friends. I'm super excited to share this interview with you. Basically, this year, this scientific paper came out that blew my mind. A bunch of scientists sat down and tried to figure out if we could detect gravitational waves from collapsing warp drive bubbles. So basically, we don't have warp drive yet, but if there's someone out there who does, when their warp drive collapses, would we be able to detect it with our current gravitational wave detectors? It's a great conversation. I got to talk to the authors, Sebastian Khan, Katy Clough, and Tim Dietrich, all with different backgrounds, all with different perspectives. We also talk a little bit about our love for Star Trek. So you don't have to read the paper to enjoy the interview. That's what it's here for. And I hope you enjoy. Thanks.
Yep. Hi, everyone. We are here with these wonderful scientists who came out with possibly my favorite scientific paper that's ever been published. And when I saw this come around, I knew we had to talk. And so I'm going to pass it first, I believe, to how I got in touch with everyone, which is because I actually formerly worked with one of the people on this paper. So Sebastian Khan, if you want to take it, introduce yourself and maybe kick it off kind of between the three of you.
Sure, no worries. Yeah. Hi everyone. My name is Sebastian Khan. I'm a gravitational wave astronomer or astrophysicist. Um, yeah, and Erin and I both worked at Cardiff University a number of years ago, which is where we met. I'll throw it over to my good friend Tim.
Hi, I'm Tim Dietrich. In Potsdam, I also work in astrophysics, theoretical astrophysics, mainly related to other stuff like black holes and neutron stars and not warp drives. And yeah, I hand it over to Katy.
Hi, I'm Katy Clough. So I'm a lecturer in Queen Mary University in London. I'm actually in the mathematics department, which enables me to do things that are a bit more crazy compared to Tim, who's our sort of serious scientist. But yeah, I work on lots of different things with gravity, the theory of general relativity, and cosmology and astrophysics.
That's great. So the paper that came out is called What No One Has Seen Before, Gravitational Waveforms from Warp Drive Collapse, which is freaking brilliant. And in the abstract, the end of the abstract, I was like, oh, these are my people. Because you say, our work highlights the importance of exploring strange new spacetimes to boldly simulate what no one has seen before. Kudos. Any Star Trek references in a scientific paper.
We actually
That was
thought
all
that
Katie.
we actually thought that the referee would make us take it out. So we put it in thinking, okay, we'll put it in and we'll see if it gets through. And we were really happy that they didn't make us cut that, because it was nice.
Brilliant. So with all of your different backgrounds, how did this the idea for this paper come about before we get into the actual science of it?
But this was you, Sebastian, so you have to tell the story.
Okay, the story's, I don't know if it's boring or not, but I was a postdoc in Hanover at the time, and Katie was a postdoc in Göttingen in Germany. And I went to visit Katie to discuss like potential ideas, what we could do, because Katie's an expert in something called numerical relativity, which is solving Einstein's equations on supercomputers. And normally we collide black holes, or Katie simulates little patches of the universe. I think I got that right, Katie, you can correct me. But I was thinking, what else can we do? Because we've got this code which literally solves the Einstein equations. And being massive Star Trek fans, as we all are, I was thinking, well, warp drives, any kind of dynamical space-time produces gravitational waves in a hand-wavy kind of way. And so whenever a warp drive turns on or off, presumably that would produce some sort of gravitational wave signal. And that's the start of it, really. Unless I missed something.
I think Tim noticed that I had a Klingon dictionary in my office. I think you were both visiting, and then Tim said, I have a Klingon dictionary too. And then we're like, oh, we're all massive Star Trek fans. And then Sebastian was like, we should do warp drives. And I sort of laughed. And then, but you were actually serious. Yeah.
That's
I had to
amazing.
learn to speak Klingon cassette tape growing up. So yeah.
I love it. It delights me to no end. This is fabulous. So I think, Sebastian, you talked about it a little bit, but sort of the science of warp drive is about manipulating space-time, and gravitational waves, we talk about sort of the trampoline, the fabric of space-time, and that when things happen or change to it, it ripples. And we have detectors that we've built on Earth that can pick them up. So the general idea of this paper is like, okay, well, we don't have warp drive yet, but scientifically, like, it is a method of traveling faster than the speed of light. So other species could be warp capable, and if they drop in and out of warp, that could give off gravitational waves, that would give off gravitational waves. Could we even detect that? Is that a way that we could figure out that there are other warp capable species out there, which I freaking love. It's like getting so ahead of the Federation, like we are now the Vulcans, to be like, I see you, even though I can't chase you. So I guess, can we talk a little bit about the constraints and limitations that you faced when trying to, so you've posed the problem now, like, can we detect warp signatures, people dropping out of warp, and the ripples in space-time associated with that? What constraints did you have to build around? Like, what limitations are there to this sort of study?
I'm going to let someone else take this because I was just the sort of, maybe not even the ideas guy, but these guys are the real experts in
No,
general
that's not,
relativity and
that's not
numerical
true.
relativity.
That's not true. So, I mean, I guess the really hard thing was the fact that we don't actually have a stable solution for these warp drives. So there's this description that's written down, and it describes the curvature of the space-time, and then you kind of by hand say, well, I need to get some matter and put it in this configuration to support this particular curvature of space-time that I need for this warp bubble. But, if you put kind of normal, or at least, kind of matter that we would normally describe in our simulations into that configuration, it will naturally just kind of disperse. And so just actually trying to model something that was just traveling through space was actually quite hard. And I don't think actually anyone knows how to do it. But what we realized is that this is kind of a feature and a bug, in that we don't actually want something that's just quietly traveling through space. We actually want something that kind of is turning on or off. And so we decided, okay, well, we'll phrase it as, there's been a warp drive containment failure, and now this warp fluid is just dispersing because this field has broken down, and we'll see what happens with that. So it was, in a sense, a bit of a hack to kind of get around this issue of not knowing a stable solution. But as I say, in a sense, it kind of worked in our favor because it's a very good source of gravitational waves.
Great. Anything else? That's brilliant. Yeah, I love it. And it looks like you kind of, basically the velocity that you were doing is below the speed of light. So we talk about warp drives as a way to go faster than the speed of light, but your velocity that you used for this, I guess that the ship would be traveling at, because their warp bubble is dispersing and the nacelles have failed, they're not able to sustain the warp drive, so they're dropping below. I mean, we're putting a narrative around this, right?
Yeah, exactly. It is, in a sense, a bit of a narrative. So we actually don't know if we can model things above the speed of light. So there are reasons that we think that it might be that things break down there. So, if you have a ship traveling faster than the speed of light, you can get closed time-like curves. So in principle, you can use it to travel backwards in time. And in our simulations, those kind of closed time-like curves should lead potentially to instabilities in the formulation. But what was more of a barrier for us was actually just the resolution of the simulation. So as you go to higher velocities, you have to use much more resolution, and it's much more challenging to simulate. Well, I think we plan in future to investigate whether this is really an issue. I don't know. Tim is looking skeptical. Tim, are we going to investigate this in the future?
In a few years, yes. It took us a long time to do this, right? I mean, it sounds very short and fun, but actually doing the whole computation took several years. I don't remember when we met actually in Göttingen, but it was 2018 or 19.
Yeah.
Yeah,
So it took several years. Of course, we didn't work on it non-stop. But the mathematics and so on turned out to be significantly harder than I think we all thought when we had this first discussion. So I do think it will tackle this problem, but with some time.
So there's two sort of problems then going forward. It's that the faster you go, it becomes harder to resolve, it becomes harder to model. And then once it breaks the speed of light, then does the physics kind of break down, or has that just not been solved yet? I know you talked about sort of the time-like curves, and that's sort of, trying to describe world lines and causality, and there is a barrier which we call the speed of light for how our mathematics work. And so are people working on like how to reform some of these physics equations for faster than the speed of light, or is that you guys?
Yeah, I mean, so I think unfortunately it is us, guys. It is like literally us. So, actually it's really not been studied. So in principle, I'm not aware of any argument of why so it's a question that's called well-posedness of the equations. So it's actually like, are the equations solvable from some initial condition? So I start with, my bubble of warp drive, and I want to know what happens next. And this property of well-posedness is what determines whether we can really do that or not. And we believe that all physics is kind of causal in a way that most systems should be well-posed. But as far as I'm aware, as I say, there isn't any kind of proof that once you take the space-time beyond the speed of light, it would actually break the well-posedness. But it's such a complicated nonlinear system of equations that I think it's not obvious, and it definitely hasn't sort of been studied in detail. So most sort of mathematical studies of well-posedness are done for linear systems and much sort of simpler systems of equations.
Okay, because
A lot
sorry,
of the
Tim, go on.
equations also, sorry, a lot of the equations also that radioized, I mean, they go back to 30, 40 years ago, the idea of foliating the space-time and then evolving into the future. And there, to some extent, you have to make the assumption that you can go into the future without intersecting hypersurfaces, so without intersecting, let's say, what you call time. So some of the derivations would have been, one would need to redo them. It took decades to get them working for colliding black holes and neutron stars. So I really think that there's a physical problem in simulating everything above the speed of light with any kind of formulation that exists there right now. I think this is an issue.
Yeah, because I guess the way that I've spoken about warp drives from a fictional Star Trek fun time standpoint is in the broader mathematics, more the thought experiment mathematics of it, the rule is like when you're on the surface of space-time, you can't go faster than the speed of light, but nothing says that space-time itself can't move faster than the speed of light. And so so what you're saying, and that's why we put a little ship inside a bubble, and then that bubble carries you faster than the speed of light. But really, it sounds like the mathematical actual problem solving comes down to like the time component. It's always the time components.
For our simulations, yes, it's the time component. I think in general you could do this. I don't think that there's an issue in GR to do this, on general relativity, but for our computations, I think there would be a severe issue.
Okay, great. So those are sort of the parameters that we've set up then. We're going slower than the speed of light because our warp bubble is collapsing. Yes. And it was, about what, 10 to 40% the speed of light, it looked like, about up to possibly 50%. Okay. And then I also noticed you did a size of the bubble, which was about 1 kilometer, which there's a footnote in the paper that would contain the Enterprise E. Who chose the Enterprise E?
I think it was Tim. You chose the Enterprise E, right? But I had to look up the reference, because so Tim said we need a reference, and so I had to go and look up the reference for it.
There is a reference, Drexler and Clark. We've made technical manuals and all of these things. So Tim, is the Enterprise E your ship? Is that your favorite?
It's one of my favorites. I like it a lot. I mean, we needed to have a size, and I mean, a bit of prey would have been also cool, but we needed to justify our 1 kilometer bubble.
Yeah.
You hit it perfectly.
Yeah, it kind of worked well because so 1 kilometer comes up a lot in like astrophysics because it's the size of a black hole of the mass of our sun. So it's the sort of the size of the event horizon. So we kind of wanted to stick to that kind of scale because we know the numbers in those kind of units. But then, yeah, it turned out that it was also the perfect size for a ship.
Enterprise. It'd probably be a little bit big for my little Voyager, my Intrepid class science ship that could. It'd probably be a different one. But that's interesting. So with the black hole, made out of the mass of our sun, a 1 solar mass black hole with the event horizon is 1 kilometer. Did that make it easier because you have those formulations already in your models to some extent of like distorting space-time on this scale? Did it make it easier?
I think it just gives us more intuition for it. Like, we know in those kind of units, like how much stuff we can put in one place before we start to get black hole formation or something like that. And we know the kind of resolutions that we need to resolve things on those kind of scales. So it just gave us a more intuition for what we were doing compared to our day jobs doing black holes and neutron stars.
Right. So we have the Enterprise E traveling at warp. The warp bubble becomes unstable, so they start slowing down to drop out of warp. And then once they're about at 0.1, 10% the speed of light, the warp bubble collapses. What did we find?
It's kind of a sad story, right? Because actually the first thing we find is that it's really bad for the people in the ship. I mean, unless they've got something, else that we haven't modeled to protect them. It seems like this distortion of space-time just kind of rips through the ship or where the ship would be. And so it would be really catastrophic. So I guess when in Star Trek, they're all panicking because it's warp drive containment failure. They really should be panicking because it really looks pretty catastrophic. So that was the kind of the first thing that we noted, is that it was very bad for the people in the ship. But then what we were really interested in was, what happens further away? Like, what would the signals be? Tim, you can tell us about that because you're the kind of LIGO gravitational wave guy.
We didn't leave yet. So what happens is that there is a very short burst of gravitational wave. So there's this burst-like emission, which then travels out. Of course, the question is, can we see this kind of burst? First of all, it's relatively strong, stronger than intuitively I would have expected in advance. But it turns out to be at a very high frequency. Very high frequency means on the hundreds of kilohertz regime, which is way above what current gravitational wave detectors are sensitive to. This means that so far, not seeing any warp drive signal means nothing yet. But yeah, this is the story. Short pulse of gravitational waves travels through, can be seen even rather far out, not just in our galaxy, but even further out, but not with the detectors that we have.
Got it. See, that's what surprised me the most, was that it's such a strong signal that you could basically, not just our quadrant, but the entire Milky Way galaxy, which is basically the setting of Star Trek, barely go outside of the galactic barrier. We can talk about that later, but that you could detect them, but it's at a frequency that is outside of the barrier. So kind of for people who might be trying to think of like what that means, we have microphone detectors, or however we want to phrase that, here on Earth, and this is just far outside of the ability to pick that up. So that surprised me. And what was interesting, because I'm thinking about all of these stories that we have, and the burn, in season 3 of Star Trek Discovery, was this idea that all the dilithium is rendered inert. So all of the warp drives basically go critical. Their matter-antimatter reactions exponentially increase, and then the warp drives all go catastrophic. So all I can picture is when the burn happened, not only did all of these ships fail, but like all of space-time
was shaking. Yeah, definitely. Yeah. I mean, I think we were kind of happy and sad that it wasn't within the range of current detectors. So I don't know. I think I was sad and Tim was happy. And Sebastian, you were kind of agnostic to it, because actually we wanted Sebastian to do all the data analysis on, he could have taken all of the LIGO data and, made some templates and looked for this in a search. But then sadly, because it's not in the right frequency range, unfortunately, he wasn't able to do that. But I think that was a relief to Tim, because he would have, you could imagine the follow-up paper where we say we found something and then, that's going to be pretty controversial. So
I would have been surprised if we found something. So I mean, I'm skeptical in seeing this in the first place. But also to put this in perspective, I mean, we see this far out, I mean, up to a megaparsec or so, but all the sources, the astrophysical sources that we see and detected, they are significantly further away, right? So we see gravitational waves actually from much further away than we would be able to detect warp drives. So this is also just important.
Yeah, so you talked about the burst waveform that comes from this, and we have colliding compact systems, so a neutron star and a black hole, or a black hole and black hole. Those are all similar waveforms that change just based on the parameters of the size of the black holes or how far away they are and all of that. If you were to change the size of the spaceship or how fast it's going, would this still be the same waveform? Is this something you could search for, or is it like truly a burst that it's just like a almost random? Obviously it's modeled, but it's not, it's something that's going to be unique for each configuration that you have.
So it would be always a burst. This is just from the way how, I mean, what's happening there, that basically there's a containment failure and then there's a burst of radiation. So this would be this kind of burst-like signal. But what would change is actually the frequency. So the frequency would be adjusted if we have a larger ship. So I think, I'm not sure whether we discussed it among us or whether we actually put it in the paper, said you would need a planet-sized ship. And then it would be in the frequency band of LIGO and Virgo. So not just the 1 kilometer, but significantly larger. And then it's at lower frequencies, which makes sense. The smaller the ship is, the higher is the frequency of the burst that comes out.
Right, right. So going forward then, do we have detector plans? Do we have gravitational wave detectors that are being built at these frequencies? Because this is up in kilohertz, right? Hundreds of kilohertz.
So at the moment there isn't any planned detector in that range. So there are quite a lot of proposals to try and build them in that range. So the astrophysical motivations aren't that strong in that regime. So they're, it's things like primordial black holes. So, things that form naturally from stellar evolution, they would be at the kind of LIGO range, which is why the current detectors were built to detect at that frequency. So trying to look at higher frequencies, you are looking for more exotic things. So you are looking for primordial black holes. You're also looking at signatures from cosmology, from the early universe. So there were actually quite a lot of people who are advocating for detectors in this range for fundamental physics. They're not currently talking about aliens, but maybe we've given them an additional boost. You never know. So yeah, currently definitely nothing is funded. There have been proposals, and the technology exists to do it. So it's not a question of not having the technology. It's just a question of, we have this whole frequency range of gravitational waves that we could explore. And of course, the science case is much stronger at the lower frequencies where that you're going to have sources. So unfortunately, looking for aliens hasn't convinced anyone yet.
Yeah, so close. So that's the story of how we would find other civilizations who are falling out of warp from the gravitational wave signatures from their ships. In the paper, you talk a little bit about the limitations to warp drive itself from our own physics knowledge, things like negative energy, like you said, this idea of being able to actually move through. For all of you, I guess, what's your opinion on how, because we've got a ticking clock down to April 5th, 2063. So 38 years and some change to get our act together. One of the things I like talking about warp drive is the idea that mathematically it's possible, but by 2063 or in the next few hundred years, what are your thoughts on the actual ability and what's stopping us from getting there?
Okay, I'll go first because I'm probably the most optimistic of all of us. But even I think that we're definitely not going to get there by 2063. So, I mean, I guess I kind of always want to highlight how much we don't know, about the universe, and especially about quantum physics and the sort of the interface between gravity and quantum physics. So, we have to have this negative energy density to create warp drives, and we don't really know how to create that or how to create large amounts of it. But actually, we have experiments on Earth. So there's something called the Casimir effect, where you have two conducting plates and you can generate a region of negative energy between them. So we know that actually having positive energy is not like a sort of fundamental law. It's not a hard rule that can never be broken. It's possible that it's something that could be broken kind of temporarily. And then, overall, you would compensate by having positive energy later on, and averaged over time, you would be able to temporarily have a negative energy density. So there are these energy conditions that we consider to be, things that probably should be obeyed on average, but we're not sure like how solid they are in terms of, they can never be violated. And in fact, as I say, we know that they can be violated in some situations. So given that we have all of this lack of knowledge, my hope is that, we would be able to understand in some way how to generate larger amounts of negative energy density. And we have problems in the universe like dark energy that we don't understand. And not only don't we understand it, but it seems a lot smaller than we expected it to be. So all of these things, I hope, may lead us to deeper understanding that could potentially give us a way to generate negative energy. But yeah, it's definitely on the sort of hundreds of years, if at all. And now I'll let Sebastian and Tim say maybe the opposite.
Oh yeah, no, I totally agree with Katie. I really hope that someone thinks of a way how to generate negative energy or exotic material, which has negative mass and negative energy. It's just crazy to think about. But even if you did have that, it's the enormous amount of energy you need to create a warp bubble is huge. So space-time is, suppose we call it, very stiff because it takes a lot of energy to perturb it in any way. That's why you need merging black holes to even create tiny ripples in space-time. So how do you even gather all of that energy together in the right configuration at will to create the warp bubble as and when you like? It's a hard problem, yeah.
And I stop being probably the most critical one. I don't think it will be possible.
No.
There are too many things. It's true that you locally can create effectively negative energy, but not on the entire scale of the entire system that you then have to consider. And as Sebastian said, you would need so much energy to then locally create a small negative energy bubble to then create a warp drive that afterwards you still have to compensate for this. I mean, I think the project and the idea and so on is awesome. I love Star Trek, and I would love to be wrong, but I'm very skeptical that this would be possible.
We got two different hats on. It's fine. And we still haven't discovered dilithium. We still haven't, there's lots of things that could get us there. It's all the unknowns. So, but I do appreciate, it's always good to have someone like that who's just like, no, and then that drives us to prove you wrong and find something else. So, yes, no, I appreciate that. Let me see if there's anything else on the paper that I missed that you want to mention. Anything scientifically before I talk about Star Trek for a little bit?
I mean, just to sort of talk more generally about negative energy, although Tim's very skeptical about it. I guess, you know, one of the things that we found exciting was just that this actually is one of the few studies that does try and study spacetimes that contain negative energy density. Actually, a lot of the formulations that we use for studying fluids don't allow us to study these kind of exotic matter spacetimes. And that's just a technical problem. It's not because there's any real sort of issue with it. It's just the way it's been formulated. And so what this showed us is that we could actually go ahead and do that. And there are a lot of interesting problems in physics other than warp drives, where negative energy can actually resolve some of the kind of paradoxes that we find in general relativity, like singularities at the center of the black holes, or the singularity at kind of the beginning of our universe in cosmology. And so we are actually thinking about it a bit more from a kind of more solid scientific perspective as a way that we could be resolving some of these singularities, and avoiding infinities in the equations, some kind of, you know, exotic matter that is, you know, triggered at very high densities or very high energies, that could then, as I say, change the way physics behaves. So I think there is some solid science behind it.
I mean, it's all solid. It's all. I mean, I'm just skeptical that it will be possible to.
We can create it.
Right?
Yeah, right.
That
Maybe the universe can create it, but we can't.
The universe might be able to. I mean, inside black holes and so on. I'm just saying that I don't think that we will have the power to do this.
All we have to do is harness the inflaton or whatever, you know. that expanded space faster than the speed of light. No problem.
No problem.
There we go. Yeah, so I guess, first of all, I mean, it's an awesome paper. I love, especially because, you know, academia is hard. We've got all these other projects that we're working on, not just our careers, but, you know, socially moving around. You mentioned you've like been at different institutions while you were all working on this in the background. What does, I guess, for each of you, like, what does Star Trek mean to you now as professional scientists? Is it something that you got into science because of? Is it something that keeps you going? I mean, personally, I watched a ton of Voyager while I was a researcher because I was just it was a good reminder of like what the future could look like as a scientist. If anyone wants to jump in on that.
I'm pretty sure that, watching sci-fi growing up and Star Trek in particular is one of the main reasons, or if not the reason, why I did astrophysics. It's in uni, so pretty influential, probably.
Is that still something? Do you still go back and watch Star Trek? Is that, does it continue to inspire you, I guess? Or once you were faced with a hard reality of negative energy, it's like, well, it all sucks.
No. No, I'm not quite as bad as Tim. No.
Tim, do you still watch Star Trek? You must do, right?
I watched Star Trek the last time, potentially this week. So I do watch Star Trek. I do like it a lot. I watched it when I was a kid, and this motivated me also for my studies. I wouldn't say it inspires me to do the work further that I do, but I still love it, and I still think it's super cool. Despite being pessimistic in the work aspect, at home I can be different.
Yeah, I guess for me, I did watch it as a kid growing up, but I actually think it sort of came to me a bit later. Like I was more sort of just generally interested in astrophysics. And I think I got more into like I watched it, but I had sort of enjoyed it as a kid. But then I started rewatching it when I was doing more astrophysics for my degree. And I actually kind of, in parallel almost sort of got into it. And yeah, I love the stories and I love the characters. And I do like the idea of this future where science seems to be like a key part of their life, in a way that it would be lovely if our world was like that, that we had the time and the energy to just be exploring the galaxy and doing science. So I guess that aspect of it really appeals to me. And yeah, I was watching Deep Space Nine last week, so I still watch them. I like to get my favorite episodes sometimes and just watch them. So yeah.
I love it. Well, that leads me to my final rapid fire questions as we're going to go around, and I guess we'll do the same order, Sebastian, Tim, and Katie. Favorite captain, favorite series?
Oh,
Yeah, starting with Sebastian.
Okay. Oh, that's a really tough one. I'll just oh, maybe Picard and DS9, maybe.
All right, I appreciate that. Tim, you got an answer?
DS9 and Kirk.
All right.
Oh, of course, yeah.
oh, I really. I really think this hard because I always think it's like asking people like, what's your favorite child, right? Like, what's your favorite captain? I mean, what
I
if they
knew
were
it was a mean question.
what if they were watching and one of them would be like, oh, if only I was your favorite captain. Like, so I would feel bad. I guess for me, so I think like you, Erin, I really like Star Trek Voyager. I guess I like Captain Janeway because she's like such a great character. And I also like the Voyager story, like the idea that they're on sort of having to get back home. So I'm going to pick Voyager and Janeway.
Nice. I mean, that was the correct answer, really. So for me it's Voyager, and like Deep Space Nine I just keep coming back to. Like Voyager holds a really special place in my heart. I'm much more emotionally attached to Voyager, but like I love the stories of Deep Space Nine. And look how Star Trek can bring all of us together. It's great.
Proper Erin factoid from Cardiff. On the postdoc door,
Yeah.
Erin had the Quarks bar paper poster. Like, I can't remember. Didn't you have that come to Quarks? Quarks is fun
Yeah.
on the door. Yeah,
Come right now. Don't walk. Run.
yeah, exactly. Always love to see that.
That was on my postdoc door. Yeah.
Yeah,
So,
you were the
yeah.
funnest postdoc for sure in that office.
I like to think so. I like to think that I brought some fun levity to the
Yeah.
environment. But yeah, thank you all for coming and chatting. This was super fun. Great paper. Congratulations. I know these side fun papers are, like you said, they take a long time because we got a lot of stuff to do, but yeah, I loved reading it. I loved talking to you all about it. So thank you all for your time, and continue the good work. We're going to find those warp drives.
I mean, I think we are still excited by real science as well. I mean, it is a really exciting time with gravitational waves. We don't know what we're going to see. We've got some, okay, we haven't got the high frequency gravitational wave detectors, but we have got some coming at lower frequencies. And, it is always like opening a new window and you don't know what you're going to see there. So I think that it is an exciting time to be working in gravity.
Well, we'll leave it there. Thank you all again for the time, and live long and prosper.
How cool was that? Oh my God. So basically, we could detect gravitational waves from warp collapses even as far as other galaxies. We just don't have the detectors in the right frequency to do so. But such a cool result, so fun to talk about. If you are scientifically minded and want to check it out, I've added a link to the paper down below. I want to thank everyone again for taking part in the interview, and I hope you enjoyed. I'll be back with some more content later this year.